Hi Math 215 students. In this video we're going to talk about an algorithm for finding the inverse of a matrix if there is one. Our outcome is just this. We want to be able to remember and apply this row reduction algorithm for finding A inverse that we're going to be seeing in the video, and hopefully you'll get some sense of why it works. We'll actually talk a little bit more about why it works in the next video, which we'll mark as optional, but this video should get you started on understanding that. So to begin with, we had some questions in our prologue video for this section. Which matrices have inverses and which do not? How can you tell? And how can you find the inverse of a matrix if there is one? We were able to answer both questions in the case of 2 by 2 matrices, but we've not talked about how to answer the question for any matrix larger than 2 by 2. That's what we're after in this video. We want to be able to take a 3 by 3 matrix, say, and figure out what the inverse should be. What can we multiply the matrix by in order to produce the identity? Now, to begin with, what we're going to do is remember one of the interpretations of matrix multiplication. We said that when you multiply a matrix A times a matrix B, your answer can be thought of as having columns that come from multiplying A onto the columns of B. If we represented the columns of B by B1, B2, and so on all the way through the last column, then AB has columns where you get the first column by multiplying A onto the first column of B. The second column of your answer comes from multiplying A onto the second column of B, and so on through the end. So what we see here in our equation above is actually what the right-hand side equals. We don't know what the first column of B should be, or the second or the third column, but we do know that when you multiply A onto those columns, you get these columns of the identity matrix. And so if we wanted to, we could solve for the columns of B to figure out what B is. I could figure out what the first column of B is by taking the matrix and multiplying it by this unknown vector and setting it equal to the first column on the right-hand side. And for the second column of B, I can use the second column of the right-hand side. And for the third column of B, I'll use the final column of the right-hand side. And then if I were to be able to solve these three matrix vector equations, I would be able to fill in the columns of that inverse of A. Now, solving matrix vector equations is fantastic because we know how to do that. We can row reduce an augmented matrix. And so if we were to solve that first column of B, remember, we know that A times the first column of B should equal the first column of the identity matrix. So we'll just tack that on in our augmented matrix and start row reducing. So if you take a look at what you might do to get a pivot position in the top left corner, we might start by switching rows 1 and row 2. We'll pivot, we'll take that 1 and multiply the first row by 3 and add it to the third row for a replacement operation. After that, I'll be a little clever here and switch the second and third rows. And the reason we do that is so that we can create a 1 in that second row in this way. We don't have to deal with fractions to get that 1. We can actually just create it as you see here. While doing some replacement operations, combining a couple there, we'll end up with this matrix, and then doing one more set of replacement operations, we'll end up with the identity matrix on the left, and that tells us that B1's first element should be 4, the second element should be 5, the third element should be -8. B1 should look like this. So that tells us the first column of our matrix B, and we're making real progress on finding that. Now let's move on to the second column. We want to solve a problem that starts off the same way, except we're using B2, and we're using the second column of the identity matrix. So if you like, go ahead and pause the video here. We'll reveal it in a second. As we get started, well, again, we want to have a 1 in the top left position, so we might start by switching rows 1 and row 2. And then we might want a 0 in the bottom, so we'll take 3 times row 1 and add it to row 3. And then after that, oh, here's where we wanted to be clever. So we switched row 2 and row 3, And what you should get out of this so far is that actually we're doing the same row reduction steps as we did before. We're going to get the same 1 there using our multiplication trick, and everything continues the same as it was. The only difference is what's going on in the right-hand column. Because we started with a different vector there, the right-hand column ends up looking different even if the left-hand side of each matrix ends up looking the same as it did on the previous screen. So we end up with the second column of B2, but what we want to point out is that the row operations we used to row reduce this problem were exactly the same row operations we used to solve for the first column, and only that right-hand column, only that last column of the matrices looks different. Okay, well at this point we've got the first column of B. We now have the second column of B. Putting those together, we should be fine. The thing you want to think about though is how would we do this more efficiently? To solve for B's third column, I know that I have to use the third column of the identity matrix on the right-hand side, but if I know that the row reduction steps are going to be the same, maybe I don't even have to write those out. Maybe I can just fill in what the right-hand column should be in each of these matrices. Remember, the same row operations can be used, only the last column has to look any different. So as we do that row operation, first we switch row 1 and row 2. I already know what happens to the left-hand side when I do that, but let's take a look at what happens in the last column. If I switch row 1 and row 2, nothing much changes. I just switch the locations of the zeros. If I take 3 times row 1 and add that to row 3, well, 3 times 0 plus 1 just gives us the same 1, and I still have the same 0, 0 as before. Now, if I switch row 2 and row 3, something will happen in that last column. Switching row 2 and row 3 will make the last column look like this. And then taking minus 3 R3 plus R2, well, that won't necessarily change the last column so much. But now when I do my replacement operations, I'm going to take the second row, multiply by 4, and add it to the first row. And that will definitely change what happens in the last column. And taking 3 of the second row and adding it to the last row, doing that in the last column will create the vector 4, 1, 3 in the last column. And then doing one more set of row operations using these numbers, you'll end up with -2, -2, and 3. Now we would have gotten these same steps even if we didn't follow that pattern. These are just what you would get if you were to row reduce the matrix. And so we know that the third column is -2, -2, 3, but we were able to do it with a little bit less effort as far as writing out these steps goes because we knew that we were using the same steps. So our question now is, could we have solved for all 3 columns of B at the same time? Instead of having to solve 3 separate problems like these, could we have done just one process that produces all 3 columns, knowing that the row operation should be the same for each of those columns? And the answer is yes, we could do that. We could solve for all of the columns of B at once. And what we're going to do is actually set up sort of an augmented matrix that has all 3 of those possible right-hand sides at the same time. I'm going to call this a quote-unquote super augmented matrix. It's just that instead of having just one column at the end, I've chosen to put all 3 of the columns of the identity matrix on the right-hand side. And as I go through row operations, I know that whatever is happening with this first vector, that's what should appear in the end in our first column of B. And whatever's happening in the second column at the end here will tell us the second column of B, and so on for the third column of B. Okay, let's see how this looks like. If I do have all 3 of those columns there, then in my first row operation, I'm going to just basically switch the entries in those first 2 rows as I normally would. Doing the next row operation we had should give you this matrix, and switching row 2 and row 3 for that little bit of cleverness with the -3 and the -8. If I do that, in the matrix, the right-hand sides, they just sort of operate as you see there. And then carrying forward with our final reduction steps, we'll do our trick, we'll do the replacements, and then we'll do the one more replacement. And what we see is that the right-hand sides, we started off copying in the identity matrix, and then we end up with this matrix. But the columns of this matrix, you may recognize, those are exactly the columns that we had found earlier for the matrix B. And so, to summarize, what we did here is start by attaching an identity matrix onto our matrix A, and then we row reduced. And at the end, we ended up with the identity matrix on the left, and the columns of that B, or the columns of A inverse, turn out to be the entries that you see on the right after all of your row reductions. So this will always work, it turns out. So here is a procedure for finding A inverse. If it has one, what you want to do is start by attaching an identity matrix of the same size as A on the right-hand side of that matrix A. Row reduce it. Your goal is to turn the left-hand side into the identity matrix using row reductions. As you do that, whatever happens to the columns at the end is good. It pushes you closer and closer to the matrix A inverse. Okay? All right, let's take this this procedure and let's try it on a bigger example. Let's find the inverse of a 4x4 matrix. Well, how would we do it? Remember, to start finding the inverse of a matrix, if the matrix has an inverse, you should attach the identity matrix of the same size on the right of it. We're going to attempt to row reduce this. We're going to try to push the left-hand side to have pivot positions in each column. We want to have that reduced echelon form, which would put an identity matrix on the left-hand side. But let's just see what happens as we do those row reductions. So to start, I know that my first two rows look okay as far as the first column goes, but I'm going to need to take that pivot position in the first row and use it to zero out the entries below it. So I might start by adding row 1 to row 3. You'll notice that as we do that on the left, we also need to do the same thing on the right. So I'd add row 1's blue entries to the third row. And then we would continue on. I'm going to need to take -2 of that first row and add it to the last row. And well, to save a little bit of time, I'm just going to copy this and let you take a look at this. Go ahead and pause the video. If you haven't already, you might try just doing this on your own without looking at the slide and then checking your work. You will find that with so many matrix computations, row operations, it is very easy to make some mistakes. And I won't tell you how many mistakes I've made as I have put together these slides. But take a look, try this out yourself, and just notice what's happening as we do the row reductions. We carry those on to another slide, and at the end of it, we do end up with our reduced echelon form. We end up with what looks like the identity matrix on the left-hand side, and on the right-hand side, we have some rather interesting looking entries, but we are told that what we should end up with, if we end up with the identity matrix on the left, is A inverse on the right. So that tells us that the inverse of this matrix A is this matrix with these rather large entries. Now, if you want to check, you're certainly welcome to, and I would recommend it. What happens if you multiply A by this matrix in either order? If you were to take this matrix and multiply that by A, would you end up with the identity in both cases? Hopefully you'll find as you do that that yes, you do. This really is the inverse of that 4x4 matrix A. Well, this algorithm is pretty powerful. It allows you to take a matrix of any size, any square matrix, and see whether it's got an inverse and what that inverse should be. So we have an answer to both of these questions. How do you find the inverse of a matrix? Well, we know how to do that. You attach an identity matrix on the right, you do row reductions, and then you see what ends up on the right. And if it has an inverse, that will guarantee you an answer. Now, what if a matrix doesn't have an inverse? What would happen if you were to try to do this procedure? Well, if you read carefully, the theorem says that if you do start row reducing and A turns out not to be row equivalent to the identity matrix, if you don't end up getting the identity matrix on the left-hand side, if you don't have a pivot position in each of those first columns, then it turns out that your matrix does not have an inverse. So let's take a look at a matrix that we know is not invertible. If we take a look at 1, 4, 2, 8, this 2 by 2 matrix, you'll see that the determinant is equal to 0, so there's no inverse. We see that actually the second row is 2 times the first row, or the second column is 4 times the first column. That's another way to recognize that it has no inverse. What if we did this process where we attached an identity matrix and just tried to find an inverse for it? Well, as we do our first row reduction step, you're going to try to zero out the 2. So we would take -2 times the first row and add it to the second row. We'd end up with a matrix that looks like this. But you'll see that because the pivot positions here actually don't happen in the first columns of the matrix, your second pivot position actually ends up on the right-hand side. There's no way you're going to be able to produce the identity matrix on the left. And what that means, what this test is telling us, is that our original matrix does not have an inverse. As we already knew, 1, 4, 2, 8 is not invertible. So you don't have to know ahead of time whether a matrix is invertible to apply this test. If it is invertible, you're going to get the identity matrix and what the inverse looks like. If it's not invertible, you're going to end up in a situation like this, where it's not possible to get those pivot positions in each column of the left-hand side. Well, that is our reduction algorithm, row reduction algorithm for finding the inverse. We've talked a little bit about where that algorithm comes from. Please review that if you're interested. And then, as we mentioned in the next optional video, we're going to be talking a little bit about what we call elementary matrices and talking about another reason why the algorithm works. I'll see you there. Let me know if you have any questions.